I did have some technical difficulties, so could not make all the videos in time. Hopefully, all those things are now settled, and I should be able to make up all these videos in a couple of days and upload it on YouTube. Okay, let us continue with our complex analysis or a function of complex variable. In this lecture, we are going to cover limits, continuity, and differentiation of complex valued function. This is a part of a course Mathematical Physics PH3103 at IISER Calcutta. Let's start with the definition of limits for a function of complex variable. It is somewhat involved definition of various terms, but we will try to visualize them. Suppose f of z is a complex valid function in the neighborhood of point z0. Suppose that L is another complex number. The limit f of z tending to z0 exists and equal to L and is written as limit f of z going to z0 is equal to L. If for every epsilon there exists a delta such that the f of z minus L is less than epsilon, then we have a delta such that z minus z0 is always less than delta. So it is a conventional mathematical definition of what is called epsilon delta definition of limit. But let's try to visualize. We have a xy plane domain of a complex function, and we have a UV plane which is the image of the complex function. We have a point z0 in the domain which is mapped to w0 in the image plane through the function f of z. Now we have a limit. It need not be same as w0. In general, it could be different. Later we will see that in the case of continuity, both will have to be same. For the definition of a limit of a function, you don't need them to be same. Let L be limit, and then what we have, we construct a neighborhood with the given radius epsilon. So whenever the function value is inside, then we can construct a neighborhood around z0 with the delta such that whenever the function value is in the neighborhood of w, the domain is inside the neighborhood of z0 with the radius delta. You can choose epsilon. It is up to you. If you change bigger or smaller, the domain delta would be bigger or smaller. All it says is that if you choose a point in the neighborhood of L, however small that epsilon may be, you would find a domain inside neighborhood of z0, and all the point would be inside. That means no point close to the limit would be mapped far away from the value of z0 in your domain. So all of this domain would be mapped in the neighborhood of limiting value L. So that is basically is a definition. Let's take an example. Function is f of z is equal to z square minus 1, z as z going to I, which is z0. And we see that in this case L is same as w because I have taken a smooth continuous function. F of z0, which is I, is equal to minus 1 minus I. Now let's define z is equal to z0 plus delta. So it's a small neighborhood around z0, and then see what kind of values it maps to from domain to image. Now we come back and see whether we can given epsilon, we can associate a value of delta and say that whenever is image is inside the epsilon, all the values of domain is inside the neighborhood with the radius delta. So we substitute z0 plus delta, and then z0 plus delta square minus z0. It should be z0 plus delta. We can simplify this. We get z0 square plus delta square 2 delta z0 minus delta. So we can take a limit delta going to 0, then we immediately see that it is taking the value of z0 square minus z, which is the value of f of z. So this function takes same value as the value of the function. Now let's try to say that the f of z0 plus delta minus z0 is less than epsilon, so some arbitrary epsilon. Then we can always construct delta satisfying this condition. Then if you choose the delta satisfying this condition, then for every epsilon there is a delta with which the z0 would be close to z radius delta. So that is how we construct the value of delta based on the epsilon given. There are some criteria for the existence of limit. Things get complicated in the z plane. In the real line, it is fairly simple. When you take the limiting case, you have one dimension, so you can at the most come from the two direction, positive direction or the negative direction. In the case of a complex plane, it is a two-dimensional object, so your approach to the z0 could be from any direction. So this may lead to several values of the limit. Say, let's say we have a z0 with the delta given here. Of course, there could be an epsilon which is bigger than this or smaller than this. In this, we are not looking at the epsilon, we are only in the domain. In the image plane, there is going to be an epsilon from which this delta is connected. So for every epsilon, there is going to be a delta with this neighborhood, and then we have a limit which could be coming from various directions from the axis or anywhere around arbitrary direction. So this leads to all path leading to z0, and it might lead to several limits. So the existence of a limit is very clear. It is called criteria of non-existence of limit. If f of z approaches to two complex number, L1 not equal to L2, for different curves or path through z0, then the limit of f of z does not exist. So in our case, more to worry about the existence of limit, what it says is that essentially all the path coming in the z plane, when the limit approaching to z0, they should define one limiting value. If there are more than one limiting value, then your function is discontinuous. Let's take an interesting example. Let's look at the function f of z is equal to z by z star. Of course, what is special about it, what is interesting about it, let's see. Let us compute our limit for this by taking the z0 and take two direction only. It is sufficient to show any two direction leading to different limit, then limit doesn't exist. To show the existence, you have to show that all the curves leads to the same point, but to show non-existence, two conditions are enough. Now we can assume that approaching z0 from a positive x-axis, that is you have delta is only real. Imaginary part is 0, then we have delta going to 0, z is a delta plus I0, and z star is a delta minus I0, so this limit is becoming 1. Let's look at another direction, that is coming from the positive imaginary axis, that is you are coming along the z axis and approaching the z0, which is a point. So here we have a real part is 0 and only imaginary part is there. So let's take the limiting case comes to be delta going to 0, 0 plus I delta divided by 0 minus I delta, complex conjugate. Now we take limit delta going to 0, it takes the value of minus 1. So two different approaching curves gives the different values of limit as z going to 0. It is clear that this limit does not exist. Homework, take a simple function z is equal to z star and work out as z going to 0 whether this function is continuous or not. So it's not the simplicity or complexity of the function which makes it a continuous or discontinuous. So let's look at some of the trivial properties of the limits of the complex function. Let f of z and g of z are the functions of complex variable. We have a limit z going to z naught f of z is equal to L, and the limiting value of g, that is z going to z naught, is m. Then the following are true. It is fairly simple to show all them. I am just listing them. Limit z going to z naught, alpha into f of z will have a limit of alpha into L unless alpha is 0. If we have a limit z going to z naught, f of z plus or minus g of z, then it would be zl plus or minus m. Same way we can multiply two function whose limit going to z naught would be multiplication of two limits. Same way division rule also valid provided m is not 0 or the function which is in the denominator does not have a limiting value of 0. Now within this context, whether you can figure out what happens to f of z is equal to z divided by z star. So you can see within this context of these rules whether you can come up with a simple explanation why f of z by z star is continuous or discontinuous based on your reasons. Let's go to continuity of function. So a complex function f of z is said to be continuous at point z naught if limit z going to z naught f of z is equal to f of z. So the limiting value now has to be the value of function itself. Then only the function becomes continuous. Let's look at the example. Consider a function f of z is equal to z square minus iz plus 2 and determine if it is continuous at z naught is equal to 1 minus I. The first thing we have to compute the limit by taking z going to z naught. The z naught is 1 minus I. This takes the value of z square minus I z2. So we substitute by putting delta. Delta can be anything coming from any point. So we have 1 minus I plus delta minus I into 1 minus I delta plus 2. You can show that as delta going to 0, this takes the value of 1 minus 3i. The second thing which need to be shown is f of z, and these two results have to match. F of z when z is equal to 1 minus z naught equal to 1 minus I is equal to f of 1 minus I, that is 1 minus I square 1 minus I plus 2. This takes the value of 1 minus 3i. So these two do match. So the function is continuous at value of z naught is equal to 1 minus I. So we have limit z going to z naught, f of z is equal to f of z naught. Function is continuous at z naught is equal to 1 minus I. Discontinuity of the principal root function. So we have earlier seen the definition of principal root as z to the power half is equal to square root of modular z e to the power argument of z by 2. The double valid function, we have taken only principal component, that is argument of z only. The other values are ignored, and then we call it a principal square root function. So let's look at what happens to this function on the unit circle. Let's assume that the mod z is 1 and square root of that is also 1. So we have z to the power half is equal to e to the power I theta by 2 or cos theta by 2 plus I sin theta by 2. So we have a plane here, xy plane or uv plane, where I plotted the z is equal to minus 1. We have to essentially compute the limit and the value of the function. If the function is approaching from a different path, whether it lead to similar result or dissimilar result, that is what we need to see. So we can approach the z-axis from two direction, positive theta direction, that is coming from the positive y-axis, and negative pi direction, and that is coming from the negative y-axis, and see what happens to the case. Let's first take the case of theta approaching from the positive side of the pi, and then we have a square root of z, limiting value theta going from positive direction of pi. We have a cos pi by 2 plus I sin by 2 as a limit theta coming from positive side. We have this value is equal to I. So this is going to be 0, and then from the positive theta, that is pi by 2, we have this becomes 1, and then we have I. So let's come from the negative direction. This again becomes 0. We have a negative side here because we are coming from the negative side as a angle coming from the minus pi. So we get the value of minus I. The function z to the power half is discontinuous at the value 1. So it may be true from the all point in the negative z axis because the limit is coming from the positive pi and negative pi, and then you would see it is becoming discontinuous. All along the negative x-axis you would see that this function is not continuous. Have a homework problem. Show that the polynomial functions are continuous in the entire complex plane. So we have a polynomial function of p of z is defined as a an zn an minus 1 zn minus 1 plus so on, and plus a1 z plus a0 constant term, as this function should be continuous in the entire complex plane. Branches of the complex function. A branch of a multivariate function f of z is a function small f1 of z that is continuous on some domain, and that assigned exactly one multiple value of f of z for each value of z in the domain. For a multivariate function, we can have a multiple values of a function for a given value of z. Now we have often seen that several examples in which we can create a domain in which it takes the single valued function, and then using a Riemann surface or some such construction, separate them and construct a domain in which the function takes a single valued, and that is what we call is a f1. And we completely forget rest of the values which are multiple. So we can restrict to this single valued function in the restricted domain. That called the branches. So we have seen z to the power half. We have seen that the one value which takes it is from minus pi to plus pi. So that is a single valued function, but it is discontinuous on the branch cut, but otherwise f of z is equal to z to the power half when restricted to the domain minus pi to plus pi. It is a continuous single valued function. So that is one branch of the function. There is another branch of function which we did not take. The principal valued function of a square root is one branch of a function. You could have many branches to the function. Let's leave this point. It is has some significance, but often we intuitively understand this, and let's not worry too much about it. One of the very important topics is derivatives of function. In order to do any physics, we need to have derivatives or calculus to be done on the function. So here let us define the derivative from the first principle. Let f of z be a complex valued function defined in the neighborhood of point z0. The derivative of f of z at z0 denoted by f prime of z0 is given by f prime of z0 is equal to limit delta z going to 0 f of z0 plus delta z minus f of z0 by delta z, provided this limit exists. It is the same definition of a derivative even in the real functions, except the complexity of that this limit need to exist for an arbitrary path approaching z0, and all the limit in value have to be same, the limit to be existing. So this is a standard definition of derivative from the first principle. We can use it for computing the derivative, but often we use much simpler rules to calculate the derivative of the function. If the above limit exists, then the function f of z is said to be differentiable at z0. Let's take a simple example. The function f of z is equal to z square minus 5z using the definition or the first principle. F of z naught plus delta z is equal to z plus delta z square minus 5z plus delta z. So you can simplify this entire expression to be z square plus 2z delta z plus delta z square minus 5z minus 5 delta z. Now we need to subtract f of z naught from this. F of z naught plus delta z minus f of z naught gives you 2z plus delta z square minus 5 delta z. Now we divide it by delta z and take the limit delta going to 0. So only coefficients with the linear in delta z would remaining. Rest of the terms with the higher order in delta z would vanish, and as a limit delta z tending to 0, we would get 2z minus 5. So this is the value of differential. We know how to do it. Differentiate this z square minus 5z would simply lead to 2z minus 5. Often we don't use first principle. We use simple rules to compute the. Let's look at the quick example. Of course, for function which is not differentiable. Let's look at the function f of z is equal to x plus 4iy if it is differentiable or not at any point. Look at that, it is not really a function of f of z in the conventional way it comes in the physics. We have created a function by an ad hoc way where when you have a z is equal to x plus iy, you have the real part x and imaginary part separately and created this function. This is not really natural function. Let z be any point in the complex plane, then you can write it as a real part and imaginary part. That is z is equal to x plus iy, and then delta z also can be written. That is delta z is equal to delta x plus I delta y. Now we have f of z plus delta z minus f of z. So that reduces to delta x. It's a simple linear function, so it should not be a problem. Delta x plus 4i delta y. We simply need to divide it by delta z and take the limiting values that going to 0 from two different paths. Let's take a two different path from which this limit approaches to 0 or delta z comes to 0. So the first path is along the x-axis and the second path along y-axis. So along x-axis we have an imaginary part 0, along y-axis we have a real part 0. So that is delta y is equal to 0 along x-axis, and delta z is delta x. Along imaginary axis we have a delta x is 0 and delta z is delta y. Now we take the limit delta z going to 0. For the part parallel to x-axis we get delta x by delta x, which is 1. For the imaginary axis we get 4i by delta y by I delta y. Because it is coming along the imaginary axis, this gives the result 4. So this limit doesn't really exist because it takes a different value for two different paths. So this function is not differentiable. Whether a real part of a complex function is a continuous or not, imaginary part of a function only is continuous or not. That is f of z is equal to real of z is continuous or not, f of z is equal to imaginary of z is continuous or not. Then you would figure out that there is no way this function is going to be differentiable at all, because these two are not differentiable function. Let's look at the simple rules of differentials which are extensively used in the case of real analysis. There are same rules valid here also. Most of the time we blindly use these rules. Only point here have to be taken into account that the validity of a limit is to be done little more carefully. But when you have a differentiable function given, then you can make a various combination of them. If f of z and g of z are differentiable at a point z on a complex plane, and if alpha be a complex constant, then the derivative rules are given by this. First rule is a constant rule. The derivative of constant is 0, that we know. Derivative of multiplication of constant to a function is a constant, simply comes out. Sum of rule is a linearity property, always have to be valid because the differential is a linear operation. Then the product rule. Product rule we have in the real analysis too. It just takes the take a differential of the first function, multiply by second function, plus you take a differential of second function and multiply by first function. You have a quotient rule. You can use it for differentiating the f of z by g of z. It is a standard form, same as in the real analysis. We also chain rule. All these things takes the standard rule as in the real analysis too. This is a standard procedure for computing the functions of differential. We often don't go to first principle unless the function itself is non-trivial. So let's continue this topic in the next video. We will have a more interesting topic coming soon, but let's stop here now.